Hi everyone, and welcome to our module on sensitivity and specificity. Before we get into specific diagnostic tests, let's define two important terms, and those are incidence and prevalence. So suppose there are 1,000 new cases of diabetes per year. This would be the incidence of diabetes. It's the number of new cases that develop over a period of time. Suppose also that there were 100,000 cases of diabetes at any one point in time among a population, then this would be called the prevalence of diabetes. Now, sometimes people calculate a number called the incidence rate, and that's the number of new cases divided by the population at risk. So it's determined for a period of time. For example, you might determine the incidence rate over 1 year of time. And you have to remember in this calculation that the population at risk is the total population minus the people with disease. So if you already have disease, you cannot be at risk for that disease. So suppose, for example, there were 40,000 people living in a given county and 10,000 of them had disease and there were 1,000 new cases per year. The incidence rate would be 1,000 divided by 40,000, which is the total number of people minus the 10,000 who have disease. So that would be 1,000 cases per 30,000 people. And you're sometimes asked to calculate an incidence rate on an exam, and don't get tripped up by forgetting to subtract the number of people living with the disease. They are not at risk. There's another term people sometimes use called the prevalence rate. That's the number of cases divided by the population at risk. And when you're doing this calculation, you use the entire population. You don't need to subtract anyone. You're looking at how many cases are there in the entire population. It's important to know how incidence and prevalence change with different disease types and when different treatments are developed. So for chronic diseases, the prevalence is generally much higher than the incidence. And to understand this, think of diabetes and hypertension. There are millions of patients living with diabetes and hypertension, so the prevalence is very high. People can live for years and decades with those two diseases. This makes the prevalence very high. Now, there is an incidence of diabetes and hypertension. New patients are diagnosed every year, but it tends to be much smaller than the prevalence. For rapidly fatal diseases, the incidence and the prevalence are often almost equal. Think of Ebola in Western Africa. People tend to develop this infection and die very quickly, so the number of people who have the condition is very close to the number of new cases diagnosed over a period of time. When a new primary prevention program is created, both the incidence and prevalence will fall. So imagine if we successfully implemented a smoking cessation program in New York City. This would lead to a drop in the incidence of new diagnoses of lung cancer, and then over time, it would also lead to a drop in the prevalence. On the other hand, if a new drug comes out that improves survival, this is going to leave the incidence unchanged, but it's going to increase the prevalence because people are going to live longer. This happens a lot of times with cancer drugs. Patients live longer with their disease, so we see the same incidence of cancer that we've always seen, but the number of people living with the disease goes up because they're surviving for longer. So now that we've defined those two important terms, let's get into our discussion of diagnostic tests. And in order to understand diagnostic tests, let's suppose that we want to come up with a blood glucose level that would allow us to diagnose diabetes. So in order to do this, we're going to measure the blood glucose levels in some normal subjects who are over here on the left side of the screen and some diabetics on the right side of the screen. And we see that in general, the numbers for the normal subjects are on the lower side. 112 looks to be about the highest. There's 115 here. Many numbers are in the 80s and 90s. And for the diabetics, the numbers are generally higher, as we'd suspect. So there's numbers like 160 and even 199. So they're all a bit higher. And hopefully, we're going to be able to identify a blood glucose level that we can use as a cutoff. So we can say everyone below this glucose level is normal and everyone above this level is a diabetic. Now, in an ideal world, if we plotted the blood glucose level on the x-axis here and the number of subjects that had each measurement on the y-axis, we would see two curves that look like this. All the normal subjects would be on the left side with relatively lower blood glucose levels, and all the diabetics would be on the right side with relatively higher blood glucose levels. And if reality looked like this, we would pick a cutoff right here for blood glucose level and say everyone below this is normal and everyone above this is a diabetic, and it would be a perfect test. Unfortunately, reality never works out like this. In reality, the two curves generally look something more like this. So there would be an overlap, and this means that no matter where we put the cutoff for diabetes, we are going to have an imperfect test. For example, let's imagine that we put the cutoff right here. Well, everyone above the cutoff would have diabetes, so that would be good. All these diabetics would be picked up by the test. but not everyone below the cutoff would be normal. We'd have all these diabetics who are below the cutoff, and they would be classified as normal. So this test would have many problems. Now let's imagine we put the cutoff right here. Well, everyone below the cutoff will be normal, so that's good. But above the cutoff, there will be many normal patients who will get classified as being diabetic. Look at all these people here would be classified as being diabetic. And if we put the cutoff right in the middle, then we would have a mixture. So below the cutoff, all the people classified as normal would include a lot of diabetics, all these people under the red curve here. And above the cutoff, which would be diabetics, would be many normal patients, all these people right here. So when the curves overlap, there is no ideal cutoff, and you're going to have to accept some degree of false positives and false negatives in your test. And this is the way reality often works. We just have to do the best we can with diagnostic tests. So let's imagine that we make our cutoff point right here. So everyone below this point is going to be classified as normal, and everyone above this is going to be classified as diabetic by our new diagnostic test. Well, if we choose this for the cutoff point, we're going to identify 4 groups of patients. The first group are going to be what's called the true positive. These are diabetic patients who are identified as positive for diabetes by our test. So that's going to be all the people under this red curve that fall above the cutoff point right here. And we're going to call them the true positives. A second group we're going to identify are the false positives. So all these normal subjects who fall above the cutoff point here are going to be classified as diabetics, even though they're normal. So these are going to be false positives. We're also going to identify a number of normal subjects who fall below the cutoff point. So these are appropriately classified normal subjects. These are true negative patients. So all the people under the blue curve here that fall below the line, these are all going to be true negatives. And then finally, we're going to identify a fourth group, which are all these people under the red curve that fall below the cutoff point right here. All these people are going to be false negatives because the test is going to say they don't have diabetes, but in reality they do. So the way we analyze the performance of a diagnostic test is by taking those 4 groups of patients, true positives, false negatives, and true negatives, and writing them in what is called a 2x2 table. And this is an example of a 2x2 table right here. So along the top, we have disease presence, and the patients who are positive for diabetes are here on the left, and the patients that are negative are here on the right. On the side, we have the test results. So the patients that are positive are written along the top row of the test, and the patients that are negative are written along the bottom. And we write the actual number of patients that fall into each category in each quadrant. So for example, the number of true positives might be 50, and so we would write the number 50 here. The number of true negatives might be 25, so we would write the number of 25 over here. So what we do to create this table is take normal subjects and subjects with disease, like I showed you in the example for diabetes, choose a cutoff point and count up the number of true positives, false negatives, and true negatives, and write it in the table right here. Once we've done that, we can calculate several numbers which give us characteristics of the test. And the first one is called sensitivity. So the sensitivity of a diagnostic test is equal to the true positives divided by the true positives plus the false negatives. And the easy way to remember it is that it's everything on the left column right here. The trues always go on top, so true positives go on top, and the total of the two always go on bottom. And this is how you calculate the sensitivity of any diagnostic test. So let's go back to our 2 overlapping curves and look at what the effect of different cutoff points would be on the sensitivity of the test. So if we chose a cutoff point that's very low over here, way down at a low blood glucose level, that would be a very sensitive test. And let's think about why it would be very sensitive. It would be very sensitive because you would have a large number of true positives. Look, this cutoff point would identify every diabetic subject as a true positive. So the number on top in the sensitivity equation would be very large. And the number on bottom is going to be the true positives plus the false negatives. But if you look at this cutoff point, there are no false negatives. Everyone who is identified as negative by this test is a true negative. It's a normal subject. So this cutoff point way over here on the left gives us the maximum number of true positives, the minimum number of false negatives, and that is going to maximize the sensitivity of the test. Now let's talk about a cutoff point way over here on the right. This would be a not very sensitive cutoff point. And let's talk about why that is. Well, the number of true positives would be relatively small. Of all the diabetics, only this small group here is identified as true positives. So this will make the top number in the equation relatively small. And then the bottom number is true positives plus false negatives. And look at all these false negatives. All these diabetics right here are getting classified as false negatives. So this cutoff point way over here on the right is going to make the sensitivity very small. And this is where you put the cutoff points for tests that are not very sensitive. Now let's talk about the second metric of diagnostic tests, and that's called the specificity. So the specificity is equal to the true negatives divided by the true negatives plus the false positives. So for the specificity, you're going to just focus on this column on the right. Remember, it was the column on the left for sensitivity. It's a column on the right for specificity. And remember, just like for sensitivity, you always put the trues on top, so the true negatives go on top, and then the total of the column goes on the bottom, so that's true negatives plus false positives. So let's look at what some different cutoff points would mean in terms of the specificity. So a cutoff point over here on the right side of the two curves would be very specific, and let's talk about why that is. Well, the true negatives go on top, and let's look at the number of true negatives at this cutoff point. The number of true negatives is huge. Every single normal subject is going to be appropriately classified as a true negative by this cutoff point. And then the denominator of the equation is true negatives plus false positives, but let's look, there are no false positives. There are no normal subjects on the right side of this line. So choosing a cutoff point over at this side of the x-axis gives us the maximum specificity. On the other hand, choosing a cutoff point on the left side of the two curves gives us a not very specific test. And let's talk about why that would be. So the true negatives are on top, and we have a small number of true negatives here. They are these normal subjects that I'm highlighting right now. On the bottom of the specificity equation is true negatives plus false positives, but look at all these false positives. All these normal subjects here have been identified as false positive. So choosing a cutoff point over here gives you a very low true negative rate and a very high false positive rate. This leads to a small specificity. So here's a sample question that you might be asked. The results below are obtained from a study of test X on patients with and without disease. What is the sensitivity of test X? So remember what I said, when you're asked for sensitivity, just focus on this column on the left side. It's always the trues on top, so the true positives are the 25 patients, and then it's the total on the bottom, so that would be both added together on the bottom. So the sensitivity of this test is going to be 25 divided by 100, or 25%. And if you were asked for the specificity, you just focus on the column over here on the right. You're sometimes shown the two overlapping curves for normal patients and patients with disease and asked to select the cut point that maximizes both sensitivity and specificity. And you should know that it's going to be right in the middle where the two curves overlap. Why is that the case? Well, remember, to maximize specificity, you want the cut point way over here. And to maximize sensitivity, you want the cut point way over here. So the happy medium where the two together are at the highest levels they can achieve is going to be right in the middle. You should also know that the degree of overlap of the two curves limits the maximum combined sensitivity and specificity. So remember that an ideal test would have a normal group of patients that looked like this and a disease group of patients that looked like this, and we'd be able to choose a cutoff in the middle that was perfect. It perfectly divided the patients into normals below it and disease patients above it. Now, there is no such test like this, but the closer we get to this ideal situation, the better our sensitivity and specificity. If we had an ideal test like this, it would achieve a 100% sensitivity and 100% specificity. So the closer our data look to this ideal situation, the higher their combined sensitivity and specificity are going to be. So let's look at these two data groups here. Look over here on the left. There's a lot of overlap of these two curves. So the maximum combined sensitivity and specificity for this test is not going to be that great. But let's look over here on the right. These two curves have very little overlap, just this little bit down here at the bottom. So this group of patients with this diagnostic test is going to be able to achieve a much better combined sensitivity and specificity. Just remember, the closer you are to that ideal situation where the normal and disease patients are completely separate, the better the performance of your diagnostic test. So now let's talk about a very important and high yield key point, and that is that high sensitivity tests are very good at ruling out disease, and high specificity tests are very good at ruling in disease. And let's talk about why that's the case. So recall that I said a cut point down here on the lower side of the x-axis is a very sensitive cut point. But let's talk about why that would be good for ruling out disease. Well, everyone that is negative from this test here is a true negative. So if you are negative with a very sensitive test, you most likely truly are a negative disease patient. On the other hand, if you're positive with a very sensitive test, you may be a true positive because the test picks up a lot of true positives, all these red patients here, but it also picks up a lot of false positives, all these patients under the blue curve right here. So a positive test result on a very sensitive test doesn't mean that much. It's very hard to tell whether that's a true positive or false positive. But a negative test result in the very sensitive test is extremely helpful because most of those patients are going to be true negatives. For specificity, the situation is the opposite. Recall that I said a high cut point over here is a very specific cut point. And if you are positive on a very specific test like this, which means you're above the cut point, you're most likely a true positive. The only patients that are positive are diabetics. So a specific test gives you a test result that's very specific for diabetes. On the other hand, if you're negative from a very specific test, it doesn't mean that much. You may be a true negative, like all these patients under the blue normal curve here, or you may be a false negative, like all these patients under the red curve here. The negative result is not that meaningful, but the positive result is very meaningful and is most likely true. So let's suppose you want to find a rare disease among a big population. Let's suppose there's a new disorder called rare OMA out there, and it's highly deadly, but if you catch it early enough, you can treat it. Well, most of the patients you're going to test for rare OMA are going to be negative. It's a very rare disease. So you want to screen with a sensitive test so that you can believe the result. Remember, the majority of the population will have a negative result because it's a rare disease. You want to be able to believe that test result, and that's why a sensitive test is the one to use. Now, the sensitive test will identify a mixture of false and true positives, so you will follow up the positive screening test with a specific test. So this will let you sift through the false and true positives and let you get down to a small group of people who most likely really do have that disease, rare OMA. And this is the way we screen for a large number of diseases in medicine. We use some very sensitive tests so that if it's negative, we can believe it. But then if it's positive, we say to patients, well, you need to go and have a second test to see whether your result was a true positive or false positive. Now here's another very important and high yield key point. Sensitivity and specificity are characteristics of the test, and they remain the same no matter what the prevalence of disease. And this is going to be especially important later when we talk about positive predictive value and negative predictive value. Those two metrics change with prevalence, but sensitivity and specificity do not. So to make this point clear, let's consider a hypothetical situation. Suppose test X has a sensitivity of 80% and a specificity of 50%. And suppose we test it on group 1 where the prevalence of disease is 80%. Well, anytime you're faced with a question like this, what you need to do is create 100 imaginary patients. So I'm going to write the number 100 right down here. And then I'm going to split them up in terms of disease positive and disease negative patients based on the prevalence. So if the prevalence is 80%, then I'm going to write the number 80 right here. And if 80 of the 100 patients are over here, then the other 20 must be right here. So 80 represents the total of all the patients in this column, disease positive patients. And 20 represents the total of all the patients in this column of disease negative. So now that we've decided there are 80 patients in this column on the left with disease, we have to split them up into test positive and test negative patients. And we do that by the sensitivity. So 80% of the patients go on top as true positives, that's 64. And 20% of the patients go on bottom as false negatives, that's 16. And you can see that these two numbers add up to 80 so that we're staying consistent. For the column on the right, we're going to use the specificity. So the specificity is 50%. So we put 50% of the patients down here, that's 10, and 50% up here. So now we've completely filled out this 2x2 table. And this represents the distribution of patients in group 1 where the prevalence is 80%. Now let's repeat this exercise for group 2 where the prevalence is 20%. So once again, I'm going to write my 100 imaginary patients over here. But this time I'm only going to put 20 of them on the left side in the column that represents disease positive, and I'm going to put 80 on the other side. However, I'm going to distribute these 20 patients among the two quadrants, once again, based on the sensitivity. So 80% of them go up here, that would be 16, and 20% of them go down here, that would be 4. For the 80 patients who don't have disease, I'm going to split them up 50-50 because the sensitivity is 50%. So 40 of them go here and 40 of them go here. So what I've done now is created two 2x2 tables. One is for group 1 where the prevalence is high, and the other one is for group 2 where the prevalence is low. So now I've moved those two 2x2 tables to their own slide, and we have group 1 over here on the left and group 2 over here on the right. And now I'm going to calculate the sensitivity and specificity. So the sensitivity for group 1 is going to be this column right here with the trues on top, so 64 on top, divided by the sum of those two quadrants on the bottom, that's 80, and 64 over 80 is 80%. For the specificity, we focused on the right-hand column, so that's going to be the true negatives, which are 10, over the total, which is 20, so 10 over 20 is 50%. Now for group 2, we do the same calculation. The sensitivity, we focus on this column here. It's going to be 16 over 20 or 80%. The specificity is this column here. It's going to be the true negatives of 40 over the sum, which is 80. So it's 40 over 80, and that's 50%. So you can see that the sensitivity and the specificity are identical, even though the prevalence in group 1 was 80 and the prevalence in group 2 was 20. And if you don't want to remember all this math, just remember the point I'm trying to make, which is that sensitivity and specificity are independent of the prevalence of disease. A word about the language that's often used in question stems. You may see the following: a test is negative in 80% of patients who do not have the disease. What they are telling you is the true negatives. People who don't have the disease and test negatives are true negatives. So they're saying that 80% is the number that goes right here. If this number is 80%, then this number must be 20% right here. And from these numbers, you could calculate the specificity, because remember, specificity concerns this column on the right. You may also see a test is positive in 50% of the people who do have the disease. They're describing the true positives, so that means that 50% is the number that goes over here, and that means that the false negatives must be 50%. And from these two numbers, you could calculate the sensitivity. Now recall that a few slides ago I said that if you use a sensitive test, it's very good for ruling out disease, because people who test negative are usually true negatives. But the implication of that is that sensitive tests are very good when we don't want to miss cases. Sensitive tests capture many true positives. Now they do this at the cost of false positives, but if we don't want to miss cases, we're willing to pay that price in order to capture as many true positives as possible. This is why sensitive tests are good for screening large populations, especially for severe diseases that can be treated if they're picked up early. Now, once a sensitive test is positive, we usually follow that up with a specific test. These are called confirmatory tests, and this is the way screening of large populations is often done, because the sensitive test does not miss any cases. And that concludes our module on sensitivity and specificity.